Okay, so I'm here to talk about sound design for auditory alarms, more specifically for healthcare environment auditory alarms. As an introduction, as most of us know, what an alarm is, what an auditory alarm is. Those are the just like the fire alarms we have everywhere that can trigger when a certain threshold is crossed, indicating is that something is not well. So the same happens in healthcare environments when we're monitoring a patient. For some reason, a threshold is crossed and an alarm is triggered. Why auditory alarms are important? Our hearing system is available to us 24-hour non-stop. We can't shut it down just like we can with our eyes. And it has an advantage that it can monitor on a sphere around us, so omnidirectional, almost omnidirectional sphere around us. We can monitor the state of our environment and localize sounds. This is useful because in an healthcare environment or in other working environment, we don't need to actually be looking at a certain device. If an auditory alarm gets triggered, our hearing will get it and redirect our attention to it. The focus of the work is in auditory alarms for healthcare, and why? Because there's a number of reasons where alarms in the healthcare environment are not detectable by the professionals, and past research has identified this. One of them is just the desensitization of professionals due to a large number of false alarms, false positives. Also, in this kind of environment, there's a lot of alarms going on all the time. So for an experienced worker, his brain automatically tunes out, and sometimes alarms that are important and shouldn't get tuned out, say, go undetected. Another reason is the sheer amount of noise on the environment, noise that can be from other alarms, HVAC systems, people talking, etc., that render some alarm inaudible. And this is the focus of the work. It's called, on a more technical or scientific slang, called masking. So masking is when a louder signal, sound event, renders another one inaudible. And we're all familiar with loudness. If you look at the picture here on the mall, we can imagine that our phone, if it rings, we might not hear it. There are several dimensions on the effect of masking. Spatial, which I won't be talking in detail here. Temporal, as well, is not relevant for this presentation. And spectral content of the signal, that's what we're going to talk about, is spectral masking. Spectral masking is, as said before, a loud sound masks a softer one when they happen in simultaneous temporal conditions. And what do we have if we graph this sound events here along frequency and on the horizontal axis and power on the vertical axis? We have a masker. I'll get my pointer here. We have a masker sound, and we have a masking threshold that indicates that any sound that happens to be below the masking threshold most probably won't be audible, and any sound that will be above the threshold will be detected. So if we have a sound event, I call it mask EB, that is well above the masking threshold, it will most definitely be heard. And if we have a sound event that is above the threshold but not significantly above, is within a region, it will be detected most of the times because it's above the masking threshold, but due to interference phenomena, it might not be perceived with high fidelity. Its loudness is in fact reduced. So in the healthcare environment, since the early 90s, these devices have been improved, and nowadays they are capable of reproduction of much complex sounds all along the frequency range or substantial range of the hearing frequency range. So that gives the sound designer an opportunity to work with these sounds, which are no longer simple bleeps and buzzes, and try to avoid spectral masking by spreading components of the alarms through the frequency range. So as I said, if we put components in spectral regions that are sufficiently distant apart in frequency range, this will be audible and won't be masking one another. So this study has implemented a method to aid the design of auditory alarms, and the application concerns on a recent standard update, this standard that gives guidelines for sound alarms in healthcare environments. The model is based on a psychoacoustic, the method is based on a psychoacoustic model. And this slide just quickly to say what is this. So psychoacoustic models are based on experimental data, lots of it, and they relate physical properties of the sound event with our perception, so hearing sensations. So masking is a hearing sensation, and interference as well, and loudness as well. So this is the type of perception we are dealing here with. It all happens in our hearing system. A sound comes in and travels along our hearing system, our ear canal, and in the cochlea. Research has demonstrated that different parts of the cochlear hair cells on the basal membrane resonate at particular different frequencies of excitation. So a Bark scale has been developed, which maps these positions in the basilar membrane here. So it has 32 millimeter length. Maps them to frequencies of the stimulus. And this is this works as a spectrum analyzer, a series of bandpass filters, which can be seen here. So what happens? Once again, we have an event at a determined frequency that excites a determined region in the basilar membrane. If we have an event that excites the very same region, but at an intensity such that it doesn't result on an increase of excitation that is significant, our brain won't detect it. This is the phenomenon of masking. What we're going to do, we're going to implement this spectrum analyzer and this physiological behavior on a mathematical model, and for that we are taking advantage of the MPEG developed psychoacoustic model that they've used on their standard codecs for compression. Very quickly, our method separates components in noise-like and tonal components and takes advantage of additivity to calculate a global threshold. We're going to try to analyze an alarm of this recent standard with our implementation, our method, and see if we have masking. More specifically, we want to guarantee that a high priority alarm is never masked by a medium priority alarm. Fairly confused graph, but we'll go over it. On red, we have the masking threshold of the medium priority alarm. So anything that is above it is estimated as audible. Anything that is below it is inaudible. So what we have here fundamental frequency of a high priority signaling. And it is above the red line, so probably it's going to be heard. Here we have harmonics, additional harmonics of this sound event that signalizes a high priority is approximately in the same position as the red line, a bit below, so maybe not so detectable. Here we have an icon that tells us that there is a problem with oxygenation, and it is far above the red line, so for sure it's heard. But it's, if we notice, it's far above the high priority as well. That might not be reasonable, say. So what we can do, well, we can decrease the energy in this region, overlapping regions, and as said before, we don't like overlapping regions on the basilar membrane, so we can decrease this energy and let the fundamental be heard, and we can increase the energy of the icon here a little bit so it gets closer to the red line, so it can be detected. Most importantly, the high priority signal, we want it to be well above the red line. Here we have a plus 12 dB on the threshold. Above that level, it is definitely hearable, so it will be detected. And we might also want to add one harmonic, so it is in the region of 12 dB as well. So the higher priority signaling is most definitely heard. Thank you. References and thank you. That's it. So sorry for going 3 minutes more than established.
Thank you. So I think now it's better because we can see you.
Yes.
So please, to the audience, I ask if someone wants to make a question. Now it's the right time. Gostaria de perguntar, portanto, se a audiência tem alguma questão a colocar na sequência da apresentação que acabamos de assistir.
Pode ser em português ou em inglês, estejam à vontade.
Eu tenho uma curiosidade, é uma pergunta, mas é mais para satisfazer uma curiosidade. Eu gostava de...
Sim.
O vosso problema, no fundo, acaba por ser algo muito concreto, que depois tem uma grande complexidade pela quantidade de variáveis que influenciam não só capacidades cognitivas, como inclusive outros aspectos físicos que intervêm.
Exato.
Um pouco melhor, portanto, como é composta a vossa equipa.
Diga, não, falhou o áudio.
Gostaria de saber como é composta a vossa equipa em termos de áreas, de especialidade.
Portanto, nós somos uma psicóloga com experiência também em usabilidade. Eu, portanto, formado em acústica e um sound designer, portanto, para o desenho dos sons. E com isto, esta é a equipa core, digamos. Estamos a trabalhar também com outras pessoas que auxiliam em, por exemplo, testes neurofisiológicos de detecção de sinal, e teremos em breve também outra pessoa para juntar-se à nossa equipa da área da acústica.